Okay, so this section is going to introduce some of the basic types of reactions for organic molecules. And then what we're going to do when we get to alcohols, ethers, aldehydes and ketones, carboxylic acids and esters and amines and amides, again, sort of similarly with the prefixes and, counting the long chain, all that kind of stuff, you're going to see patterns, okay? So then, so we'll have an official lesson for this, and then the patterns will repeat for the other families, okay? So, um, we did sort of talk about the first point yesterday that organic compounds have very strong covalent bonds. So the reactions for organic compounds are often very, very slow, and they require a continuous input of energy. And so I talked about how if we were going to do the reactions in class, that many of them, we would have to use the stock hydrochloric acid. You would have to heat them up in a water bath, so the inputting the heat, except combustion. Organic molecules will readily burn, okay? So we're also going to talk about what happens when you get a mixture of products. And um, so what happens is if you choose to become some sort of organic chemist, then you actually have to figure out what is the mixture, what's the percentage of one product over another product. And then so they have to be separated and removed, which takes even more time. So there is, the simplest way to get something apart, like sand and water, you could just use a sieve or a colander, right? Whereas when you have two liquids, then you have to distill them and separate them based on boiling point, which, say the two liquids are the same color, like clear, then those lab procedures have to be much more precise. So again, every time you're trying to be as precise and accurate as possible, then it costs time. Okay, so alkanes, because they have single bonds, are less reactive than alkenes and alkynes. Aromatic hydrocarbons, which have benzene, are more reactive than alkanes, but the double bonds are not going to break. I'm not going to ask you to rank based on reactivity, but you'll see that we're going to look at more reactions that involve double bonds than single bonds. When you are trying to decide where is the reaction going to happen, then you're looking for the reactive site or where is the functional group, okay? So if there is a double bond, if there's a OH, when we do alcohols and ethers, if there's a C double bond O, that is going to be much more reactive than just the hydrocarbon chain, except of course when we do combustion. So it is important that you remember you need oxygen to burn something. Okay, so if it says write the combustion reaction for ethane, it's not going to tell you necessarily that you need the O2. You have to remember that. Sometimes your textbooks will ask you to write reactions and they'll use the structures. So they draw oxygen like this. It's Lewis structure for whatever reason, which is fine. It's just showing you O2, right? It's diatomic. And then we're just going to assume complete combustion. If you're asked to write the reaction, you know that that's not always the case. So even gasoline you pump in your car, then you can get unwanted products like carbon monoxide and carbon. But the thing with incomplete combustion, so normally, again, we did the mole unit in grade 11, and you could predict how much product was made and all that kind of stuff. Normally, most reactions you can't just have a random mix of the amount of reactants. There's like this minimum, right, limiting reagent, this minimum amount that you need, except for combustion. So incomplete combustion occurs when there's not enough oxygen, but but combustion is such a of certain molecules is such a readily occurring reaction that it will actually work even if there's not the correct mole ratio. But if you're asked to write a reaction, then just assume that it's complete. So the products are always going to be carbon dioxide and water. So you can do whatever. We'll do methane, which is the gas, that's natural gas that comes out of our taps. The gas taps at the back, if you have a natural gas heater in your house, most people have a natural gas furnace. If you live in the country, you might have propane or oil. That's just a hydrocarbon with differing numbers of carbons. So methane is one. You don't really have to worry about states when you do this. Plus oxygen, you're going to get carbon dioxide and water. And then you just have to balance it. So we need 4 hydrogens, and for all the other reactions we're going to do, we are going to draw them out. You're not going to have to write an equation like this. And for some of the reactions, because they get very complicated very quickly, we're going to simplify it to introduce you guys here that we're actually going to leave them unbalanced as well, because it gets very complicated very quickly. But combustion you've seen before. Yes? Without the red 2s? Yes. So then, because I wanted to make 4 hydrogens, then I put a 2 here. 2 times 2 is 4, which makes 2 oxygens. So then 2 plus 2 is 4, so then you can just put a 2. If you, let's say it was still an odd number, you could balance using fractions. That's not an expectation. You don't have to do that. Okay. So the first type of reaction based on single bonds is substitution. So if I was sick, they would have to replace me. So that means that whatever you have on the chain is being substituted. So something comes off and then something else has to go on. So you can look for, in an alkane, if it's just a hydrogen, then it doesn't matter at all. Or look for the functional group that's being switched. And then you want to make sure that carbon still always has 4 bonds. So if you take something off of carbon, you want to make sure you put something back on. Same with me. If I wasn't here, they would have to put somebody in my place. So substitution is single bonds. Whereas when we do addition, those will be double or triple bonds. If you like the general formula of a reaction, then you have 2 reactants and 2 products. Again, that's going to be different than addition as well. And we're going to substitute hydrogen atoms with halogens. So again, we need the most reactive atoms possible because these reactions really don't want to work. So fluorine, chlorine, bromine, those are very reactive atoms. F for fun, right? Fluorine is the most reactive nonmetal. And what you get produced, a fancy word, is called an alkyl halide. And what that means is a carbon chain or an alkane, remember only single bonds, so only alkanes, with halogen atoms. And we call that an alkyl halide. So again, reactions with fluorine are the best, but chlorine and bromine, if you heat them up or give them light energy, they'll work as well. Okay, so what will we do? Let's do ethane. So if you want, when you have ethane, ethane has hydrogens, and they're all the same, okay? I'm going to pick this one, so just pick one and make it a different color if you have different colors. But all of these hydrogens are equivalent, okay? Okay, so all the H's are equivalent. I just picked this one because it's going to be closest to the F2. It is important here to remember that when you're trying to figure out what the other product is, that, what are they called? Halogens are all diatomic. So it's F2Cl2Br2. So that will help you predict what the other product is going to be. Okay, so if on ethane, I take away this hydrogen, and remember, I just picked one. You don't have to pick the same as me if you prefer a different one. Now this, if I take that hydrogen away, then this chlorine only has 1, 2, 3 bonds. So it's missing a bond. So that means that we need to put something on it. What are we going to put on it? We're going to put fluorine. We want the hydrogen has to go somewhere. Where's it going to go? With the other F. Yes. It'll be one of them, Cl2, Br2, or F2. So I just picked F. It could be Cl2, it could be Br2. Usually in the questions, it'll tell you the reactant and, sorry, the two reactants, and then you would do the products. Sometimes it'll be like, they'll put a question mark here, but they'll give you the reactant and the product, and you have to figure out what it is. That's a little bit trickier. But most of the time, they tell you the reactants, and then you just have to figure out the products. So pick a hydrogen to remove. All of these are the same. Then put if you take the hydrogen away, this chlorine needs a bond. You put the fluorine on. Then you have H, which is 1, and you have +1, and F, which wants to gain 1. So they go together nicely, and we're good. Okay, so it does follow the rules that you're used to. Because we're doing halogens, then all of them want to gain 1. And because we have hydrocarbons, which are carbon and hydrogen, then the hydrogen wants to lose 1, right? Or share 1. So it all works out. Okay? So now this, usually you have to write the name. Okay, so this is 1 fluoroethane. Okay? Usually we're not really stressed about what the other product is. This is not an organic product because it doesn't have carbons, but you can put hydrogen fluoride. And then just in case you see these terms, so an alkane with a halogen atom, so that's this. So this is an alkyl halide. and this is a hydrogen halide. Normally, your textbook questions will just be write the reaction between ethane and fluorine. Sometimes it'll say, if they're fancy, how do you produce an alkyl halide and a hydrogen halide or whatever. These orange names, you don't have to write. If it says draw and name the organic products, it means this, like what we practiced yesterday. 1-fluoroethane and the structure. Yes. In this case, because it doesn't really matter, it might not. But when it's more, when we do like the alcohol one, it might, yes. Yes, yeah. Okay, so on the summary sheet, the chart that I gave you, it says I gave you the general reaction. So if you want to write an example, you can. So we did an example of combustion. We did this is an example of substitution. That's the kind of thing that you can fill in this chart. This isn't for homework. This is just to help you. So if you don't like this, you don't want to do it, that's fine. But you do have to know the reactions for the test, okay? But we're going to do substitution for alcohols again, so you're going to see it again, okay? Okay, so when you have benzene or aromatic hydrocarbons, then they have different substitution reactions because the double bonds in benzene don't break. And actually, like Lauren just said, we often don't draw the little hydrogen in, right? So in this picture, I've drawn it in. Why did I pick this one? Because that's what your textbook does. When you have a ring, there's no beginning and no end. But in case you're a textbook reader, I thought, okay, I just made it the same as what they do. Okay, you could have picked this one, you could pick this one. All of them have one hydrogen. So we're going to do the same thing. Substitution, you have to switch. If you take a hydrogen off, you have to put something on the chain. And in this case, the chain is benzene. So there are 3 choices. So again, it could be any halogen, like Jovan said, why did I pick hydrogen? It could have been bromine or chlorine. If you forget what the halogens are, if you use the pink periodic table, it tells you the groups at the bottom. It'll remind you that the halogens are here, okay? So wherever it's basically the same thing that we just did. The hydrogen's going to come off. And then the F will go in its place. Similar to the other example, all of the hydrogens are equivalent. Again, in all 3 cases, I picked this one because that's what your textbook did. But especially with a ring, there's no beginning and no end, right? So they really don't matter. They're all the same. Okay, so in order for an organic reaction to occur, you really need a strong acid. So nitric acid is a very strong acid, and it's so strong that it actually has to be stored away from other acids. So students often ask, is it only going to be nitric acid? And the answer is yes, okay? So when you have nitric acid, you have to remember one of the functional groups that could have been substituted or could be on the chain. So there was a slide yesterday and it talked about chloro, fluoro, bromo, and then one of them was nitro, okay? So when you see nitric acid, it's going to put the nitro group onto the benzene, okay? So I will write that out. So it won't be sulfuric acid, it won't be phosphoric acid, only nitric acid. Nitric acid is reactive enough to do this kind of reaction, okay? And so when you put nitro as the functional group, then you're going to kind of do atom math, okay? So if we subtract NO2 from HNO3, what are you left with? So I take away an H, take away an N and two O's, what are you left with? HO or OH. And what is HOH? H2O, water, okay? So in grade 11, and again, I can't remember if I emphasized it online or not, I really encourage you to think of water as HOH and not H2O, okay? Even in double displacement reactions, that's how the ions switch when you do acid reactions, and you're gonna see it here. When in doubt, for an organic reaction, and even when you do biochemistry in grade 12 bio, the other product that's not the organic molecule is often water, okay? So here, again, it's always going to be nitric acid. You do need to remember what nitro is, okay? So that's NO2. And then you subtract the N and two O's, and you're left with OH, which is water, okay? So then this becomes nitrobenzene. And water. Number 3 is the weirdest one because most students want, because of this, they'll want to put on this benzene the chlorine. And actually what happens is whatever the carbon chain is, in this case it's 2, usually it's like 3 or 4 practically, it wouldn't be humongous, but whatever the carbon chain is, that's what gets on the benzene. So since this happens to be 2 carbons, which is F, then when you put the carbon chain on, whatever size it is, then it becomes ethyl benzene, okay? So these benzene reactions are, like maybe this one's like the substitution one, but these ones are pretty tricky. So they're definitely in the homework, but generally speaking on the test, I would give you all of this and ask you to label the kind of reaction, like substitution. Normally, I don't make you write out these reactions because they are a little bit weird. And when we do even if it was not Corona, we were going to do the organic labs. You saw in that video, benzene would make you vomit, right? Like the smell is so bad, it's so toxic. So we're obviously not going to use it in the lab. So then you guys don't get an opportunity to practice. So it's extra ruthless, okay? But there are definitely, like you could definitely recognize it and say, oh, this is substitution versus addition or combustion, whatever. One more weird thing about this, and I feel like it's one of the homework questions. You can get double substitution with benzene. So remember we did OMP, ortho meta para. And what happens is, maybe I'll try. I'm gonna sneak this one down here, okay? Because I think it's one of the questions in the homework. So double substitution for benzene, you want to use meta, okay? Which is 1,3. So if you have to put another chain on, like say it already starts with 1, okay? So if we call this number 1, then it's going to go, meta is 1,3, or it'll go like skip a spot. So most people will go clockwise because you're used to clockwise and would call this number 3, but you could go counterclockwise and call this number 3. That's fine too. I believe in your textbook, even for this year, it'll be the same thing. So you could do double substitution with a different functional group, but we won't do that this year, okay? And this is definitely a question in the homework. I promise I won't make you do that on the test. Okay, so single bonds, substitution, you're going to remove something and you have to put something else on. You have to substitute or switch them in order to make sure that carbon has 4 bonds. So wherever you remove something, that's the carbon that needs something to be replaced. When you have a double bond or a triple bond, then you're going to use what's called an addition reaction. So here I really tried to not, like, here it says HNO3 as a reactant means the nitro group is substituted. It sort of looks like it's being added to the chain, but addition is saved for when you're actually adding atoms and nothing is removed. So when you change a multiple bond into single bonds, then 2 carbons are affected. So unlike substitution, addition reactions, then you have 2 compounds and only 1 product. So that's one of the differences. For addition reactions, you are looking for a multiple bond. Double or triple, we'll do examples of both. And because 2 carbons are affected, then you're going to have no loss of hydrogen atoms. Okay, so that's why we only get 1 product. Okay, so we'll do different examples because there's a whole bunch of things you can add to the double bond or triple bond. And again, these happen a lot more readily than the substitution reactions. So hydrogenation, for example, so instead of just calling it addition, they actually give it a name, and hydrogenation is a reaction that breaks the double bonds, and that is a what's the word I'm looking for? Like, again, if you're into nutrition, it's sort of a bad word, right? Hydrogenated fats, because their double bonds have been broken. So now they're more like saturated fats and lie together like solids in your arteries, and they can cause problems with heart attacks. So these reactions occur so often that they've actually given them separate names. So I just did it, again, if you're a textbook reader, it looks like your textbook. If you were asked to state the type of reaction, you can just put addition. You don't have to say halogenation or hydrogenation, okay? But your textbook does, so I kept it like this. So this is halogenation, which is just addition with a halogen. Hydrogenation, addition with a hydrogen. So they're just being extra specific, okay? So I'll just start with the simplest. So I'll do halogenation with ethene. Yes. Reaction, sorry, it's just a short form. Reaction. So I'll do halogenation with ethene, and then I'll do hydrogenation with ethine. So if you like the triple bond, so I hope if you printed the notes off, this space is a little bit bigger than this one, and that's on purpose, okay? So I'll show you both. So I'll draw out all of the hydrogens, and again, but you don't have to do that. Jovan, if you want, Sean's not coming today, if you want to sit up here. Yeah. Or you can even sit like in Mike. Mike's not coming either, like even closer if you want. It's up to you. So I'm showing all of the hydrogens to emphasize what happens, okay? So pick the halogen you want. I'll pick bromine. Okay? So then again, when you do these questions, try to think, okay, if I have a double bond, what would happen? Well, double bond can make a single bond, okay? So let's do that. Sometimes it's called breaking the double bond. Sometimes they'll even be fancy and say adding atoms across the double bond, which is just very fancy. If you have a double bond, it can make a single bond. Then single bonds have to be broken or substituted, okay? So when you, now, if you look at this here, this F molecule here, there's a problem, right? This carbon, 1, 2, 3. This carbon, 1, 2, 3. Both carbons in the double bond or the triple bond have not enough bonds. So that's why we call these addition, because you have to add atoms to the chain. Nothing is going to be substituted. So you need a bromine here and a bromine here. I chose to draw my hydrogens in the bottom. I could have drawn them in the top. That doesn't matter, okay? If you prefer words, okay? So addition reactions change double bonds or triple bonds into single bonds. That means both carbons in the bond need atoms added to make 4, to get to 4 total. So because this is a triple bond, then we're going to go, I'm going to write it in 2 steps. But again, it's really similar every single time. As soon as you see a double bond or a triple bond, then maybe you can just write the final answer. That's fine. Sometimes the textbook will write excess, which means that the triple bond, that it's sort of emphasizing the triple bond is going to go all the way to single bonds. Okay, so if ethine, you add 1 hydrogen. Okay, so I'm going to do the same thing like I did up there. I'm going to do 1 at a time. Okay, so I'm going to do double first. It doesn't matter. Pick the top, pick the bottom. But if I'm going to go all the way to single, I need another hydrogen. Actually, I'm going to even make this a different color. So if you prefer to just do one step, then how many hydrogens do we need? 1, 2. You can do that as well, okay? Normally, the reactions are double bonds to start with. That's much more common. So we really try to, I could write whatever I wanted to on a piece of paper, right? But we try to make the questions practical for you. Yes. Usually, yes. You're asked to draw and name, yes. The organic ones only, like if you write HOH and don't write water, that's fine. Good question. Yes, Andrew. Because I showed it as 2 steps, like this becomes this, plus hydrogen to become this. Does that make sense? You don't, like I said, let's say I gave you ethyne plus hydrogen. You could just do this once you're good at it. You don't have to go through the steps, but maybe you want to. But usually the questions are not triple bonds. Usually they're double. Yes. Yes. Because we always want carbon to have 4, right? So if we take away a bond, then we have to add something to the chain. And the bond will always be between 2 carbons. So each of these carbons will need something. If you do it once, then they need 1 hydrogen. If you do it twice, then you need 2. And usually the question would say excess. So again, emphasizing that you're going all the way to single. Okay. So what happens when you have something like a hydrogen halide? Again, so those would be like, that is supposed to be an R. And we're going to see this again when we make alcohols in the next lesson. So if you have something where the chain is a little bit longer and has a double bond, so we'll do propene this time. Pick 2 colors, if you have. So in all the other cases, we added Br2, Cl2, H2. They were the same. What happens if it's not the same? So we're going to break the double bond and make it single. Okay, so I need to add H and I need to add Cl. So we have 2 carbons. Which one gets the H? Which one gets the Cl? So the way that you decide, so they're called isomers. How do you pick which one is formed? It's called Markovnikov's rule. So obviously named after a person named Markovnikov. So you can just, sometimes I've abbreviated in the solution, I just write Mark's rule. Okay? So when you add something that's got 2 different atoms or functional groups, so here, hydrogen halide like H and Br, we're going to see it when we do the alcohols and ethers lesson, HOH. So again, encouraging you to think of water as HOH. So when you add those, then the rule is the rich gets richer in hydrogens. So your eyes have to focus in on the atoms that were part of the double bond because they are the ones that are missing a bond. So how many hydrogens does this carbon have? 1, 2. How many hydrogens does this carbon have? 1. Already there. Do I care about this carbon? No. It's not part of the double bond. 1, 2, 3, 4. It's already full. We're not putting anything on there. Okay? So which carbon is richer in hydrogens? The first one. Yes. This one. Okay? So that means this carbon gets the hydrogen. And this one, oh no. I'll rewrite that. That's the quote. So now this is 2-chloropropane. Yes. No, not at all. No, if you like that better, no problem. Okay, it even gets worse than that. Yes. Oh, Michaela? Yes, we never really say where the H's are. No, yes. And if you want, like you don't have to draw it out like this, like you could write, if you're into condensed CH3, like you could do that still too. Okay, so even more annoying, we call this 2-chloropropane is called the major product. But the minor product doesn't follow the rule. So on a paper and pencil task, is this annoying? Yes. In real life, is this annoying? Yes, because this reaction makes a mixture of both. So again, you would have to figure out, is it 50-50? It's not, but it's more like, 70 and above to 30. And you would have to make sure if you're making a pill that's active inside humans, you have to make sure your mixture is correct for the dosage. So these reactions are very, very difficult and take a lot of precision and accuracy and time. So I'm going to write it out. I'm not even going to use different colors. If you get a question like this, you would just follow the major product, okay? But I'll show you the minor. Oops, that's not for me. Sometimes it doesn't matter. Like say it was hexene and it was 3-hexene, the double bond was in the middle, the carbons would be equal, so it wouldn't matter. Yes. If you were just given this question that said write the addition reaction, just follow the major, okay? Just if you see it talk about minor, what are the two products, then technically it would be, you would write both of them. But if you're just writing the reaction, just follow the rule, okay? Yes. Yes, the only time you would write the minor is if I said, what are the major and minor products? If it doesn't say that, just do major, okay? And usually I wouldn't trick you. It'll say, write the major, write the minor, if I wanted you to, okay? Okay, so one more application of this is called a polymer. So polymers they can be synthetic, like nylon is a polymer. They can be natural proteins or polymers. Anything that's a big molecule. Come in. Oh, you're looking for Andrew, right? No problem. So what I'm going to do, I'm going to show you an example, okay? But really, for the test or whatever, addition polymers, they have a double bond, okay? Similar to an addition reaction. Maybe I would make you recognize it. I'm not going to make you write it out. But they are kind of neat, and it is really, like I said, if you choose even biochemistry, then these polymerization reactions are actually important. So we'll do styrene to make polystyrene. Okay, so when you have carbons and hydrogens, and then what you want to do, okay, double bond, I'm going to change it to single bonds. When you do that, when you make a polymer, you put these units together. So poly is many, mono is one. So a monomer unit is one of these, and then you put them together to make styrene or styrofoam. Poly, many, styrenes. Okay, so you follow the pattern. So carbon, carbon is going to join carbon. On this carbon, then. Okay, and you would have many of them. So the way that we write that is n, repeated n times, just like math, like a sequence or series. But I will not make you do this on the test. Okay, that's just kind of cool, and again, an application of this kind of reaction. Okay, so there are a bunch of reactions here. I'll put the D2L version up as well. And technically your break is until 10:35. I think that's kind of annoying today. If you need a little brain break right now, nobody is out there, so not even grade 9s and 10s yet. Go, like, if you need to get a drink, go pee, whatever, do it now maybe, and then come back and do some work, okay? If you want to fill out the summary sheet first, you can do that. It's up to you.